You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Robert Nemiroff. Dr. Nemiroff worked at NASA's Goddard Space Flight Center before joining Michigan Tech. He has worked on the microlensing phenomena and is currently trying to limit attributes of our universe with distant gamma-ray bursts, whilst also investigating the use of relativistic illumination fronts to orient astronomical nebulae. In 1995, he co-created the Astronomy Picture of the Day with NASA. Hello, listeners, viewers, Horizonauts. Dr. Nemiroff's book is available in the Event Horizon Book Club over on Amazon, where you'll find selections of tantalizing, thought-provoking literature from all our previous guests and some of our personal favorites. And if you decide to purchase through Amazon, you'll be supporting the show. So thank you.
Dr. Robert Nemiroff, welcome back to the program.
Thanks for having me.
Now, Doctor, you have, as a physicist, spent a whole lot of time thinking about the speed of light and all of the weird corners and rules and things that it does that sometimes even skirts what we normally think of as C. One of these is apparent superluminal motion. So we look out in the universe with the James Webb Space Telescope, and we see these highly redshifted galaxies and things that are confounding cosmology, or so they say, but not really. But we look at those and they appear to have superluminal motion. Why is that, and what does that actually look like? What tells us that that galaxy appears, and I stress that appears, to be moving faster than light?
Okay, well, first of all, if we see a galaxy, what we see is not moving faster than light as we see it, because light wouldn't be able to get to us. So there's a difference between how things are perceived, subjective observing, and how things are in objective reality. So in subjective observing, if you see something, the light came to you from it. So however, by the time when it emitted light and then time passed before it got to you, if we go back to the time right when you're seeing it, it's no longer where it was when it was emitting the light. It's further out. And in cosmology, in general relativistic cosmology, it's moving away faster. So at that time, it could have gone out faster than light. So the galaxies we see when they emitted their light are not moving faster than light. However, they might be now. And as I say in the book, there's many cosmologists don't know this. The redshift is about 3. So a redshift is how much things appear, the light appears shifted toward the red end of the spectrum. So when we look out, we see galaxies, we see a spectrum, we say, oh, that spectrum's shifted toward the red end. How much is it? And there could be 1, which is pretty far away, 2, which is further away. You can get up to 1500, which is the microwave background. 3 is pretty far away. But if you see a galaxy that's redshift 3, then when you see it, it wasn't moving faster than light. But if you take your laser pointer and you point it at that galaxy, your light will never get to that galaxy if the universe continues on as we think it does, in the standard general relativistic cosmology. So yeah, you can't communicate with that galaxy anymore. Now, will you ever see that galaxy disappear? Some people, well, there's a misconception. Some people think that, oh no, you can't see that galaxy, but you can. That galaxy will just sort of freeze and not evolve anymore. We will always be able to see that redshift 3 galaxy. Even though we emitted light toward it and that light will never get there, we can see the image of it that's frozen there. And that image will never disappear. Just like the microwave background. We see the microwave background more and more redshifted. It's no longer the gamma rays it was when the photons were emitted. Now it's well down into the microwave range, which coincidentally is the name of the microwave background. So, but we don't see the microwave background disappear. And we won't see that redshift galaxy 3 disappear either. We just can't communicate with it.
At the far end of the universe, 10 trillion years from now, and there are alien civilizations popping up and we're long gone or something like that, there has always been the question of what cosmology you can do in a very drastically expanded universe like that. So essentially what you're saying is that they should still be able to see the CMB, right?
Yeah.
And it's a forever record.
Yes, it will always appear to get, as time goes by, it will get more and more redshifted to the point where I guess if you go infinitely far, it's so redshifted that you can't even really detect very many photons from it. But that's a different kind of limit. But yeah, in theory, if it's continuous, you will always be able to get more and more redshifted photons from everything. So you can look out into the universe and see its frozen way. The way it's sort of like the analogy I like to give is if you drop something toward a black hole, right? It goes in the black hole. And the classical way people think about it is, well, it just disappeared. It was there, into the black, zoom, gone. But that's not really what you see. What you see is you see an image of whatever it is you dropped. In the book, it's a watch, a space watch. And you see the space watch go closer and closer to the event horizon of the black hole. But waiting outside, you don't see it pass through the event horizon. You watch the watch and say, hey, wow, that watch is ticking really slowly. And if the photons are well redshifted, but you don't see the watch disappear. And it's very similar with the horizon of the universe. You don't see the microwave background disappear. You just see it get more and more redshifted. And if there were clocks in the microwave background, you'd see them move slower as well.
Now, if you were sitting there hovering above the event horizon of a black hole and you were looking down at it and seeing these ghosted redshifting images, does that eventually, say we become a galaxy spanning, Kardashev type 3 civilization or something like that in the future, can we look at black holes and tell their entire history of what's fallen into them simply by looking at the event horizon in this manner?
Wow, okay, really cool question. In theory, you could, because you can see images of everything. In practice, again, these photons are super redshifted. There's so much stuff that fell in that things would be coming to you from slightly. So you're not getting much energy, and it's all mixed together. So in practice, you really can't, but in theory, you could.
That's interesting because also, what effect would something like Hawking radiation have on that? I mean, for example, if the black hole is actually radiating information, if you will, it's also doing that just from the actual photons that you're seeing to be able to even detect that image of what fell into the black hole. So where are the photons coming from?
Yeah, so that's a really good question. So what I was talking about is the general relativistic formulation of a black hole. Once you start throwing into quantum mechanics and evaporation, I don't really know anymore. So the answer to that is, I don't know. That's a really fundamental question that I don't know the answer to. I don't know many people who would even be willing to speculate on that. But that's a great question. Don't know. That have not included black hole evaporation in the description I just gave you.
We need to go to a black hole and test this stuff. That's where it ultimately goes. So we don't have a complete understanding of physics in general. So you have quantum mechanics on one end, and you have general relativity and special relativity on the other. And they both predict correctly up to a point, and they don't quite fit. There's a missing puzzle piece. Where do you think that is? I mean, what is a fruitful way in order to try to merge these two theories together?
Wow, really tough questions. My research doesn't usually try to merge the two. I can speculate. One example that comes up in the book is, let's say you have a galaxy, and it splits the images from a background quasar. So you see this quasar image going on one side of the galaxy and on the other side of the galaxy. But then you don't resolve the quasar image so that it actually seems to pass on both sides of the galaxy quantum mechanically. It's sort of like a two-slit experiment where a photon goes through both slits. So let's make it more simple. Let's forget about the galaxy and the universe. Let's consider the two-slit experiment when photon goes through both slits. The question is, do you get gravity from both slits, from the photon that seems to go through both slits at the same time? And the answer is, I don't know. I don't know if anyone knows. That's a very simple question. That is, you have the energy of the photon going through one slit. You seem to have energy of the photon going through both slits. Does the energy from both slits gravitate? And we don't know. I certainly don't know. And it would be very interesting to try to test. That could be some kind of possibility where people might think of some kind of way to test that, because it gets at the heart of both quantum mechanics and what gravity is. General relativity does not incorporate quantum gravity in there. General relativity would generally say by itself that the light would go through one slit or the other slit. Doesn't make a prediction it goes through both slits. That's quantum mechanics.
So the immediate question that popped into my brain on this one is, okay, so we don't really understand the gravitation of two photons going through the double slit experiment, or one photon going through two slits, rather. Could that explain dark matter? In other words, could there be some effect going on between photons traveling across space-time, then acting as waves and collapsing and all of this that could multiply and maybe cause a gravitational effect on the universe at large?
I would bet against it. It sounds like if you have two things you don't know, you can just take the one thing you don't know and have it, because we don't know how quantum gravity and general relativity work, and we don't know what dark matter is. Maybe we could just smush them all together and have it work. But there's actually reasonable estimates for things that would explain dark matter. There are dark matter candidates. There are elementary particles that are predicted by some theories of quantum mechanics that say, yeah, we should probably have these things called axions. And so there could be lots of these all over the place. And there could be other fundamental particles. There could be even big chunky black holes that came out of the early universe that we just wouldn't see because none of them are close enough to the solar system. And they could be dark matter. So there's a lot of more conventional explanations for what dark matter could be. There's even the possibility that our estimate of gravity and low accelerations of gravity might be somewhat off. That's not my favorite explanation, but there's something called modified Newtonian dynamics that many people believe, not necessarily not me, but that might give an estimate for dark matter not being really dark matter, but just being our estimate of how gravity works at low accelerations is a bit off. My bet is that it's likely some kind of elementary particles, fundamental particles, and we just don't yet create them in our colliders, and maybe we won't have the technology to create them in the technologers in the reasonable future. Unsure how we would become aware of these particles independently, but I believe the universe is awash in them and they make up the dark matter. And that seems to be more consistent with established theories of quantum mechanics than just attributing it to things like somehow in the interface between gravity and quantum mechanics.
Now, your new book, Faster Than Light, How Your Shadow Can Do It, But You Can't. You explore many different avenues on how superluminal appearance can be seen. For example, a gigantic pair of scissors the size of the Milky Way closing and two blades meeting. That point at which the two blades meet, which is really a nothing. It isn't beholden. It's not an object. It's something else. Can seem to exceed the speed of light. Why is that?
Yeah, that's a really interesting thing. So actually, I've done a little bit of, I don't know, you call it research. I publish sometimes in educational physics journals on this. So I've been hearing this rumor that, oh yeah, scissors can close faster than light. I couldn't find anything on it. People seem to whisper this rumor around. And so a student and I decided to really look into this in some detail. And it turns out that if you have your basic classic scissors, so we're not going to go up to the size of a galaxy right now. We're just going to keep it in the office, in the laboratory. If you try to close a pair of regular scissors, the problem is that the information that the scissors is closing has to go down the length of the scissor, each scissor blade. And that's confined to the speed of sound in the scissor, which is less than the speed of light. So we'll just say it's less than the speed of light. So the far end of the scissors doesn't know that the near end of the scissors is closing, and then the whole thing just becomes complicated. But one thing you can do is you can use a guillotine type scissors, where you just have something that's falling down, the whole thing is already falling, and then that's one blade, and then you have another blade that's just across that's horizontal. So then you have the upper blade is just slightly tilted. Now picture that the upper blade is not tilted at all. It's exactly parallel to the lower blade. As that upper guillotine comes down, the left part of the guillotine and the right part of the guillotine are going to pass each other at the same time. So it's like the vertex between the two went, you don't even know which direction, infinitely fast. So now let's just take that upper blade and give it a very slight angle. and then you drop it again. And now instead of going infinitely fast, it goes really fast because the left part of the blade is going to intersect the lower blade, the left part of the upper blade, and the right part of the upper blade is going to intersect the lower blade just a small fraction of a second later because it's only very slightly tilted. So in that case, the vertex zips around and it can go faster than light. There's no reason that it can't because nothing on the blade is going faster than light. It's just that vertex thing, which is a hypothetical point in the middle. That's what can go faster than light. So we actually were able to publish that. The ways to close scissors faster than light and the ways to close scissors that don't work. And it's kind of cool because people think that, well, the vertex does seem to be kind of something solid. But that also means that if you were to put like a piece of paper in there, you could actually cut a piece of paper in half faster than light. You could do it. But you wouldn't be communicating information across that paper faster than light. It would just be like punctuating it in different points. And that punctuation, like perforating it, would just move across so fast, it's without limit.
So in other words, the two sides of the paper, two opposite ends of the paper would have no idea what's happening, but the paper would be cut nonetheless.
That's exactly right. Yes. And that works.
Could you, I mean, this is one of those things that anything we do other than flashlights and, things like that, we can't really do much as far as sending things out at relativistic speeds. But could you actually use that effect if you were a gigantic, again, galaxy spanning civilization? Could you actually use that effect for something?
No, we've never found a way to, even with scissors, with laser spots, with shadows, we've never found a way to communicate things faster than light. With the guillotine scissors, the left part of the piece of paper has no clue that the right part of the piece of paper is being cut. So if you're on the right part of the piece of paper and you think that you're being cut, is going to be if you'd like to warn the left part of the piece of paper, the people who live down there, that it's going to be cut soon, there's nothing you can do. You cannot communicate that. That's just the way it is. So there's one thing I like to do is with laser spots. So laser spots can appear to move faster than light, but what is happening is you're getting, when the laser spots hit a wall, say, the photons from the laser are always moving at the speed of light. But where they hit on the wall can be it's the superposition of unrelated events. So one laser spot hits, and that photon hit the wall. That's fine. And then a little bit far away, another laser spot hits the wall that's unrelated to the first laser spot. And that hit the wall a little bit later. And there's no reason why that the first laser spot to the second laser spot, if you were to attribute a speed to that has any limit at all, because light is not going between those two spots on the wall. Light is only going from your laser to each spot, and the photons hit the wall in separate spots that are not in communication. So if you wanted to communicate to a wall and you had the laser, you could do so. You could put little code in the laser. You could put a little bat signal in the laser and move it around. And when people saw the laser, they say, "Oh, the bat signal. That means something." But if you're on the wall and you see the bat signal, you can't communicate down the wall and say, "Oh, I just saw the bat signal. That's important. We need to fight the villains." So a lot of things in superluminal motion are like that you can identify things that appear to the eye to move faster than light, but you can never use it to communicate, particularly in special relativity. And it's kind of frustrating, and it's really interesting the way science seems to get around, the inherent science in it seems to get around allowing you to communicate, but you can't communicate.
So could you characterize this, that C, and some other coincident things like gravity, but C is really the limit on how fast information can transfer. So in other words, informationless phenomena, spooky action at a distance, whatever you want to call it, can, but so long as it does not convey any information, and that C really is the speed of information transfer in the cosmos.
Yes, you can. That's yes, there's a bit of a caveat to that the information that leaves the laser can't get anywhere faster than light. But if you have a bat signal and you're moving the bat signal across the wall, you can say, well, that bat signal itself is information, and the bat signal moving across the wall seems to be showing, more and more people across the wall that there's the bat signals on. So you can say in that sense that there is information moving across the wall, but nothing that creates the information can transfer that information faster than light. So if you have the bat signal, the best you can do is speed of light. And if you see the bat signal, the fastest you can communicate that to anyone is at the speed of light. But the bat signal itself could move across the wall faster than light.
What governs it? In other words, the speed of light, as far as we can tell, has always been the same, as far as I'm aware, and leaving ideas like inflation out of this for these purposes.
Yes.
So the speed of light appears to always have been a constant. What could possibly underlie the fabric of the universe that could be defining that? In other words, what is the governor? Do we have any idea? And do we ever have a hope of finding out?
Well, that's another really good question, and I don't know what the underlying physics is. I think physics is a frontier. It's not a set of knowledge, just like most science is a frontier, and that's why scientists are happy to live on this frontier, because they can sometimes, if they're lucky, extend that frontier out a little bit more. So Einstein was the one who discovered that the special relativity equations exist, and they essentially stop things that have mass and can convey information from going faster than light. But why that is, I don't think Einstein himself would really know. I don't think anybody really knows. It's an empirical fact. Ultimately, at the bottom of everything, we measure a few basic things and then we build on them. That said, there are people who speculate that the fundamental vacuum of the universe somehow is involved in creating the speed of light limit. And there's something called the Scharnhorst effect, which says that if you were to tinker with the underlying vacuum of the universe, then maybe you could even slightly speed up the speed of light a little bit. But people have looked into trying to do that practically, and there's no way to even do it in the lab where you can really even measure that the speed of light would be sped up at all. But it's a really great question. It might be tied into the fundamental vacuum of the universe, which could be tied into the dark energy of the universe, which we've just only really discovered 20 years ago. And so we don't really know. And we're trying to learn more about dark energy all the time, but not really getting very far other than confirming that it's there with different experiments.
Now, superluminal motion, apparent superluminal motion in everyday life, there is a way that anybody can walk out and see it, and it's the night sky. And if you were not aware that the Earth is rotating very rapidly, and you watch the night sky, it would appear to be moving superluminally across the night, correct?
Yeah, so that was one of the surprising things in writing this book. I didn't realize this. So if you stand out there and you watch the sun rise and set, say you're on the equator, so that people don't say, well, what if you're on the pole? So let's say you're on the equator, the sun rises and sets, and you know the distance to the sun, and you didn't know that you thought all of that motion was just the sun's motion, you'd say, wow, sun's moving faster than light. Also, all those stars, they're further away. So those stars we see, yeah, they're really moving out there. They're real far away. They're moving way faster than light. And the one thing you could see that isn't moving faster than light, but still pretty fast, is the moon. But now we know that that's all just an observational illusion and that it's really the Earth that's turning, and the sun is actually slightly moving relative to us, and the stars are all moving slightly relative to us too, but nothing is very close to light speed. So it's all one of these illusions. But here's a segue. If you could see fast enough, you could see faster than light effects right in the very room you're sitting in. And the way you do that is by turning on a single light bulb. So let's say you go into a dark room, and so this could really happen. And then there's a single light bulb in there, and you turn it on. So a second later, the room's completely illuminated. So that's not a surprise. But it used to be dark, now it's illuminated. So somewhere along the way, there was a part that was somewhat illuminated, but then there was this illumination front that went out into the dark and made the rest of the room light. So the difference between the line between dark and light, we can call an illumination front. So if you could see at nanosecond speeds, and you get into it, it's going to be very dim, but if you could see at nanosecond speeds, you would notice that the illumination front across all the walls, everywhere, is always faster than light. But that doesn't mean that light went out from the light bulb faster than light. No, the light went out from the light bulb at the speed of light. And that doesn't mean that the light that you see bouncing off the walls coming toward you is moving faster than light. It's not. That's also moving at the speed of light. What is moving faster than light is the illumination front. And so that we didn't know that for a long time. Well, I guess anyone could have calculated it. But what's really interesting is that with modern technology, we're getting into high enough video frame rates where you can actually see that. And so who cares? Big deal. You spent all this money, you bought some fancy equipment. Good job. You saw the illumination front moving across the room faster than light. Who really cares? But you know what? It is very interesting because the exact speed that it moves tells you the shape of the walls and the shape of anything that's being illuminated. So by tracking superluminal speeds, which is very similar, it's like a cousin to LiDAR, by tracking superluminal speeds, you can get a three-dimensional picture of everything that's illuminated in that room. Whereas when you look at a two-dimensional photograph, it's just flat. Because of your knowledge of the way things are, you can say, well, yeah, that mountain's in the background and that person's in the foreground. That's obvious. But just looking at the two-dimensional photograph doesn't necessarily say that. But if you could see it illuminated by a point, you could see what is illuminated first. You can see how fast the illumination fronts move, and you could build up a complete three-dimensional image of what's going on. So noticing superluminal motion in a room is more than just curious, it's useful.
So correct me if I'm wrong. That has me thinking about the moon and the Terminator moving across the moon that we see so familiarly. Mm-hmm. Could we map the moon doing this?
Yes, in theory. Again, here we get into the difference between theory and actual experiment. So you can point your laser pointer at the moon and the police won't come and say, stop that, because the amount of laser photons that are reaching the moon are relatively few. And the amount of fewer yet are bouncing off the moon and getting back to you. Now, NASA does this. They bounce lasers off of laser reflectors on the moon, and that tells them that the moon is slightly moving it away at a number of millimeters per year as it goes round and round. So it's a useful way to measure distances so accurately, you know how the moon is moving. And theoretically, if you had enough laser reflectors on the moon, or if you could detect the very few photons bounced off your powerful laser, yeah, you could do a complete map of the moon. You'd know where all the craters were. You know how deep all the craters were. You could do everything.
Now, bouncing lasers off the moon. Now, Apollo placed those instruments there, but I think also the Soviets put them there too. Yeah. And so we still use these. In other words, and since it's the surface of the moon, those mirrors, I guess you call them mirrors, we'll be able to do that for a billion years, right? So these mirrors are going to be like the longest lived human experiment possible that we've ever done to date, right?
Well, when the astronauts landed on the moon, they stepped on the moon, they left imprints on the moon. So the moon, where did those imprints come from? They came from other blasts on the moon, from micrometeorites on the moon, from bigger meteors hitting the moon and throwing up little bits of stuff. So very slowly, the moon acquires a little bit of dust on it, sometimes called regolith. So it would be quite a while, but eventually the lunar reflectors would be covered with enough dust that they would be not so useful. Yeah. So another thing, though, you remind me of is that if you were to take your laser pointer and you were to move it across the moon, and the moon was flat on the sky, and let's say the moon was not three-dimensional. We don't know. It's a moon up there. Who knows what it is? So you see, maybe it's just this flat thing pointed to us. Some people think the Earth is flat. I don't. Some people might think the moon is flat. So if it is, you take your laser pointer and you sweep it across the moon, and then you would see the laser spot, if you could see it, go from one side of the moon to the other side of the moon. Say it goes across the middle. So the moon, though, we know, is not flat on the sky. We know that from a number of reasons. But if you were to take your laser spot and sweep it across the moon, and you could look at it very high definition, what you would see is actually very strange. You wouldn't just see it move straight from one side to the other. You would see a pair of laser spots occur near the edge, and one laser spot continue to move toward the edge it's closest to, and the other laser spot move around the other side of the moon, more or less like you expected the whole thing to do. And that's one of the things that I do in my research is my students and I study this thing called relativistic image doubling. And the reason it exists is because the edge of the moon is deeper, is further away from you than the near part of the moon. So it takes the photons longer from your laser pointer to get there. So it takes so long to get to the edge of the moon that they actually hit in the middle first. And so the middle actually lights up first, and you see a pair of, that's why you get the laser, that's why it doesn't start at the edge. It starts close to the edge, but not at the edge. Well, it depends how fast you sweep the laser pointer. If you sweep it super fast, it gets closer and closer to the center. And this is a really cool effect, image doubling, and it again occurs at usually such fast timescales that people hadn't thought to look at it. But now in our modern time resolution domain and being able to see out into the universe, and with people investigating things and more in the time domain, not just in the angular domain, my students and I think that some of this could become more and more measurable, and again, not just be novelties, but might tell us things. For instance, if we know the speed that we of the laser spot that we swept across the moon, and we can see where the image doubling event occurred. If you model the moon as a complete sphere, you can tell the radius of the moon. You can tell it's a sphere, and you know its radius. That's information that you don't get if you just thought it was just a flat picture of the moon on the sky.
Absolutely amazing. Now, looking at yourself in a mirror, you are seeing yourself just slightly in the past.
Yes.
Because of the time it takes for the light to travel. But if you were able to transport that mirror very distantly, and you were able to look at yourself, say, 40 light years away, you would see a much younger version of yourself in the reflection if you could do that physically.
Yeah, so everything you see is in the past. One thing I like to say is you can only see the past, and you can only predict the future. So what you see when you look out at that object across the room, that one, that strange one, you're not seeing as it is now. You're seeing as it was when light hit it and the light came to you. So when you look at yourself in a mirror, you're not seeing yourself right then. It's only a very small fraction of a second later, but you're seeing your past self. So you're right. Let's back that mirror off. So from the edge of the room, you kind of have to squint. I think that's me. You're seeing yourself even further in the past. And so if you could move this mirror far enough away, you could, in theory, see yourself as a child. At some point, though, maybe 40 light years away, 40 light years there, further back, you'd have to be older than 80 to see yourself as a child if it's 40 light years away. But there's an interesting, again, in theory caveat, if you had a black hole. So it turns out that light can go in circles around a black hole. That's not controversial. So that means that a black hole is in some sense kind of a bad mirror. It's hard to understand what you're seeing, but it's a mirror in the sense that light sort of goes around it and comes back. So if you had a big enough telescope and if you could understand what you're seeing well enough, you could look at the black hole and see yourself at all your ages. You can see yourself as you were, all your ages is more complicated, but you can see yourself as you were when light left you and got to the black hole and then came back. So you can theoretically see yourself at a much younger age, not only with a distant mirror, which doesn't exist, but with black holes.
Slowing light down. Now, this involves one of my very favorite phenomena of nature because I think it's actually rather beautiful. It's blue glow of the Cherenkov light.
Ooh.
So when you talk about the speed of light, you're not really talking about the speed of the photon because you can slow it down, and this is complicated. But when you do that, a particle can actually outdo it in a medium like water, and thus the Cherenkov light comes. Explain the mechanism for that, and how do you slow the light down, and how do you get that blue light from a particle moving through that medium?
Yeah, so the phrase speed of light used to refer to the actual speed that light went, but then as we learned more and more, humanity learned more and more, we realized that really meant the speed of light in vacuum. So the speed of light in something else is almost always slower. Now, there's a number of types of speed of light. There's the phase velocity, there's the group velocity, there's even called something a front velocity, but we won't get into those details here. So when light goes, in fact, the whole universe, as you get outside the Earth, becomes a pretty good vacuum. It's hard to mimic it on Earth, but it's not a complete vacuum. So the speed of light is a theoretical concept now. When you say speed of light, you sort of mean the maximum speed that a photon could possibly go, or that light could go if there was a complete vacuum there. But there's not. So even in out away from the Earth, the speed of light is not actually the speed of light. It's a little bit slower. But there's all kinds of gunk you could shine light into, like a swimming pool. So let's say you take your laser pointer or a flashlight and you put it in a plastic bag or something waterproof, and you put it into a swimming pool. Yeah, that light, the effective speed is significantly, it's about a third less than it would be out in the universe, and which is very close to the speed of light in air. So yeah, it's 1/3 slower than air. So if you had a race between light above the water and just below the water, the light above the water would win easily. But wait a second, light slows down really fast when it gets into water. But let's say you had another particle. Let's say you had a proton. Well, it turns out protons slow down really fast in water too. But there's another type of particle that's pretty good at going through water, and that's called the muon. It's a fundamental particle. It can be charged. So let's say you have a muon that goes in the water, and it's a race between a photon in the water and a muon in the water. But the muon came out of vacuum first, and so it was going the speed of light in vacuum, and then it went in the water. Well, the muon's going to very slightly slow down, but essentially it's going to be going the speed of light in vacuum in the water. But light in the water itself is not going the speed of light in vacuum in water. It's going the speed of light in water. So if you had a race between a muon and a photon in water, the muon wins. And that's surprising to a lot of people. Yeah, so particles can go faster than light in water, but particles can never go faster than light in vacuum.
Interesting, but this sort of creates a question. So if a particle can outdo light in a medium like water, this shows that the speed of light is really not about light. It's, again, going back to the speed of information transfer and all that. But in this case, how do we know that the photon propagating through a vacuum actually is hitting the speed of light? It actually is hitting C, or is it just some fraction below it, like it would be with matter? You can't attain it, no matter how much energy, because it goes to infinity. You can't attain the speed of light. Is it possible that the photon doesn't either, and that it actually is moving at some fraction less than the maximum speed possible in the universe?
Yes, I think that is possible, and I think that's essentially what's happening in my view. Even photons out in the universe they're moving. The speed of light is a theoretical limit, and nothing really goes at that theoretical limit. It can only go very, very close to it. And you would say, well, we would know that. And so many times when I talk with physicist friends, they say, oh no, for instance, photons can't have a little bit of mass, because if they have a little bit of mass, then they wouldn't be going at the speed of light. And so I say, well, okay, there's some physical principles that say that photons can't have mass. So I say, well, what experiments are those physical principles based on? And you can take those experiments and you can say, okay, well, if photons had less mass than this, would you see it? And there's always an answer that if you put the mass of the photon low enough, you can't see it in the experiments. And it goes really, really low. So the mass of those photons would be so low, it would have no effect on cosmology. It would be completely not measurable in the laboratory. But in theory, it could exist. It could have just a really, really, really small 10 to the minus 70 times the mass of an electron or so mass. So photons themselves could, in theory, have a little mass. And then special relativity is written with the speed of light c in it, which would just mean that photons are moving very, very close to c. And it's not really useful for any calculations to put in exactly how much less. They're so close to c, we'll just call it c. But it's not really c. It's very, 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 very close. It might be 0.9999 and keep repeating 9 until everybody just gets bored and goes away, times c.
Comparing that to an even stranger phenomenon that we don't really have a good handle on, except that we know that it affects everything we do, gravity. Changes in gravity propagate at the speed of light. So you pluck the sun out of the solar system, Earth will find out 8 minutes later. Mm-hmm. But other than that, does gravity itself have a speed, and does that depend on whether there actually is a particle associated with gravity, or if it's something else, different force that has no particle?
Okay, well, once again, you're getting into the edge of what humanity's knowledge is. So there is no quantum theory of gravity. We can draw some analogies to things that there are quantum theories of. So according to general relativity, which is well tested, gravity essentially is related to geometry. And so geometry itself doesn't have a speed. However, geometry can change. So you might ask, what speed does the change in gravity go? And so that is something that's debated. And so one way you can measure that is with something called gravitational radiation. So just in the past few years, we've been able to measure gravitational radiation with these really long arm observatories spread out now in the world, but in Washington State and in Louisiana. And you can actually see gravitational waves from, say, black holes spiraling into each other from halfway across the universe. So there has been one event where we saw not only photons, but gravitational radiation from the same event. And they both arrived within a couple seconds of each other. So experimentally, it seems that photons and gravitational radiation have very, very close to the same speed and just be assumed to be c. Now, general relativity has the speed of essentially gravitational radiation built into it at c. But one might say that general relativity is an excellent theory of gravity, has not been, but is not a quantum theory. So if you were to throw in quantum mechanics, what then is the speed of gravity? And again, it's geometry according to general relativity, and the changes in gravity appear to be the same as the maximum information transfer, as you pointed out, which is c.
Now, time travel, but before we get to that, another question. One of the major questions that I get is an interest, anyway, in whether the photon experiences time. Does it?
Well, not being a photon again, so I'll keep giving caveats here. A lot of my friends think, hey, you're a photon. I say, no, I'm just a regular guy. So I don't know. So again, you get into the point. The question is, does a photon really move at c, or does it move really, really close to c? So in the easy approximation that it goes at c, then the photon doesn't see time pass. But the way I think about things, the photon only moves really, really, really close to c, not exactly at c. So the photon does see very slight amount of time passing.
Now, backwards time travel, the forbidden fruit of the universe, so far as we know. Backwards time travel is, and you can envision it by going faster than the speed of light, right? So time would move backwards. And there's been some interesting theories, especially those by Wheeler, where, you have one single electron bouncing back and forth through time. So when you're messing with the speed of light and backwards time travel, is it possible for anything to do it? In other words, let's set aside a spaceship and say, okay, well, you probably can't go backwards in time, but particles, can they do it? Is there some way you could envision breaking C and moving backwards in time?
Well, to my understanding, anything with mass is constrained to move slower than the speed of light. So the best you can do is go away and come back just soon after you start when you go really fast. However, there are quantum experiments that appear that it seems like information can go back in time, and there's actually a name for that called retrocausality. And John Archibald Wheeler, who is the person you alerted to, he came up with an experiment called Wheeler's delayed choice experiment, which seems to explore this. So here's a very simple way. This is an oversimplification of the way this works. You can do this with a particle going through two slits, but you can also do this with entangled particles. So let's say you had in the middle, between two well-separated things in different galaxies, entangled particles going off in each direction. So they are created together and they go off in each direction, and you measure one and your friend measures the other. So what happens is, are they correlated? So they could be completely correlated if there's just angular momentum being conserved, but you would not be able to predict whether your particle was up or down. But if you were to see your particles up and they were completely correlated, then you would know that the other one is down. But that doesn't mean that your measurement of up and down, you're not transmitting any information like that. So it's just the way things were because momentum is conserved. However, if you measure your particle at one angle and your friend galaxies away at another angle, it seems that the way you measure your particle would be correlated with what they measure. However, both people are always seeing completely random data. So what you see is particle up, down, up, down, up, down. And what your friend in the other galaxy sees is up, down, down, or something like that. And it's completely random. You say, I don't get any information from this. This is just noise. Later, if you were to take a key, answer key, and say, here's what I measured, and you can send it at the speed of light, your friend could get it and say, hey, yeah, there was a correlation. It seemed that when you measured something one way, I would measure something somewhat correlated over here. And how could that be? It seems like there was information that was going between these two faster than light. But neither person, you can't use it to communicate because both people are seeing random data. You're not seeing anything that allows you can't tell them who won a ball game. You can't tell them anything. You can only tell them later when you say, here's what the correlation was. And the weird thing is that this person can measure this thing, can measure their particle even before you measure yours. So in that case, it seems like that what you're measuring is affecting what they're measuring in the past. And that's why the phrase retrocausality comes in. But again, you're not communicating because both people are getting totally random data, and only can be determined later when you compare the answer keys, like, oh yeah, there was a correlation. It's a correlation, though, it's not communication. And it turns out that it seems like it doesn't matter, but that's very important. You cannot communicate in this method, even with quantum mechanics. You cannot communicate faster than light.
There seems to be a hard limit on communicating in this universe.
Yes.
Now, let me ask you this. Your new book, Faster Than Light, blew my mind, as I mentioned, and because there was a lot of stuff in there that I didn't know. Now, when you went into this and started looking into all the aspects of the speed of light, what perplexed you and surprised you the most in your investigations?
Well, I think the original reason that relativistic image doubling occurred, because I had never heard of it before. And so I was just trying to understand something. So one of the cool things about being a physics professor at a research university like Michigan Tech is that, you sort of have a license to try to figure out things that particularly having to do with physics that you should know. It seems like everybody does know. So I was thinking, you have this infinite wall and you take a laser beam and you shine it on this, you strafe it across this infinite wall. It just seems to me like I don't know where the spot occurs. So I thought I came up with a thought experiment sitting there trying to figure out, I don't understand this. So I have an infinite wall and I have a laser beam and it's pointed away from the wall and I sweep it across the wall. I would figure that the spot would first appear on the wall infinitely far down the wall. And that just made sense. And if I talked to people, they'd say, yeah, it's infinitely far down the wall. But then you start realizing that it takes light an infinite amount of time to get infinitely far down the wall. So it can't be infinitely far down the wall. But it's not the closest point, because you can see that the second closest point to the laser, because you can see the point next to the closest point is illuminated before that. So I was like, I don't understand this. I can't find this anywhere. I was trying to understand this. And I came to the conclusion that it's not infinitely far down the wall. It's not the closest point in the wall. There is a point in between. That's the first point illuminated by the laser. And I had never heard that before. And no one I would ask would say, oh, no, I didn't know that. So then I was really happy. I kind of figured this out, and it didn't seem like it was worth the paper, but I was going to pat myself on the back. But then, of course, I started asking myself, well, which way does it move? And it seems like, well, it kind of has to move the way you see it move. Like when you move the laser pointer, it has to sort of follow the place of the laser pointer. And that seems right. But then I started asking myself, well, what happens all the way down the wall? Eventually, those photons that you pointed infinitely far down the wall, eventually they're going to get there. How can that be if the laser spot always just keeps going in that one direction? And so after a long time, and just thinking, I just couldn't understand what to believe, I came to the conclusion that when you move a laser pointer across the wall like that, a pair of laser spots appear. And one goes in the usual direction toward the laser pointer like you expect, and one goes in the other direction. And that was the birth, in my mind, of relativistic image doubling, which I hadn't heard of before. Then I started looking in the literature to see if I can find it. And for a while I couldn't find it. But then I stumbled across a paper in the 1970s that was trying to explain why quasar images appeared to move superluminally. And one of the explanations they gave that was just in this little paragraph had to do with, actually, I've read that paragraph over many, many times. They understood the basic concept of relativistic image doubling, but they didn't expand on it. They just said, yeah, it can happen like that. So I kept looking, couldn't find more, and I said, hey, this is really cool. Why don't we, so I started, writing papers on it and trying to publish it. And sometimes the journal editor would say, oh, no, that can't happen. You must misunderstand things. And I've given talks where a professor in the audience would stand up and say, oh, no, nothing can move faster than light. That can't happen. But I've given other talks to other places, then they said, oh, yeah, that's really cool. And so one of the things that I got to rediscover that it's been really cool for me is this whole concept of relativistic image doubling. And then when I started getting into it, I would have students who would come by and I'd have to explain the same thing again. And so I decided, hey, let's write a book on this. And then the publishers told me, oh, no, that's, first of all, I'm always joking around. I don't know, you can't tell from here, but if you're in my family, you're annoyed enough that all my family members are annoyed enough to know that I joke around too much. So I decided, and when I teach, I try to include my humor, and my graduate students kind of know that I have a continuous sense of humor that I don't seem to give up on. So I decided to try to communicate that humor in the book as much as possible and try to leave off as much math as possible, focus on the concepts, and try to put in as much humor as possible. So this way, and this just happened this week, I have a student who comes in and we're trying to figure out something to study that has to do with relativistic image doubling. Instead of I'm trying to go to the blackboard or the whiteboard and try to do it again, I can say, yeah, you know what? Read chapter 8 and let's talk about it then. And so they did, and they asked me some questions on chapter 8. And so they did, and it just saves a lot of time. And so I'm pretty proud of the book. I've read through the book after I did the science in the book. I then read through the book, and I kept saying to myself, not funny enough. It's just not funny enough. Chapter 10, I don't think there's a single joke in there. So many times the C and D things, so I would sit there and instead of trying to get the physics better, which is like a perpetual thing that physicists and scientists try to do, I decided to put my comedy cap on and try to think, and with my family members, because we're a humor-driven family, what could make this funnier? And so pretty much every chapter, because I tried so hard, has things that at least I consider to be somewhat humorous. And the initial reviews, many of them say that they're finding some of it humorous as well. And what I like about that is it makes it more approachable. People might think, oh no, I don't want to stare at a bunch of equations, but it's really all about concepts. And I tried to introduce it with as much humor as possible by making the C and D answers just silly sometimes.
What I liked is just the question format and trying to figure out the answer to the question before reading, and see if I'm right. And that's what I really enjoyed. And the humor. Where can everybody get Faster Than Light?
Yeah, so it's available. It's available on Amazon. So if you want a one-word answer, the answer is Amazon. So just look for my name and Faster Than Light, and you'll find it. Actually, the question and answer format, I'll give you more history on that, is older than any of us here. People have been doing multiple choice for I don't even know if there's a history of that, but it certainly predates us. But one thing that's common in introductory physics classes now, particularly the very basic level classes, is concept questions. So instead of just writing the physics on the board, many introductory physics classes that you would take at most major universities now have these concept questions in the beginning. And that was sort of the idea that works well, because I've taught introductory physics, and I know that students they nod a lot and they write down the notes, and they think, well, I nodded, I wrote down the notes, I must understand it. But if you quiz them during class with these concept questions, and so what happens is all the students they have these little clickers now, but way back when I was starting to do it, they just had to write a letter, A, B, C, and D, down in front of them. And then I would go around, or they could hold it up, and I could see whether most of the class was getting it or not. And then you find out that some people get it and some people don't get it. And if most people don't get it, the great thing is you get feedback and you can slow down and then do something, a concept question that's similar but not that much different. But concept questions are actually very common in learning physics these days, and they're known to be effective because the students then don't just sit there and nod and write notes. They actually have to think about it and they have to answer in some way. And so what I started doing is, when I'm not the only one to do this, I did not invent comedy answers to multiple choice questions, but I found when I was teaching that when I would put in some comedy answers, it would make it less boring. So some of the students would say, "What are you doing? Why did you have such a stupid and silly answer? Why don't you just stick to the material?" But that's about some of the students. But most of the students, they would say, you could tell in the reviews at the end of the class, say, "Yeah, you know what? Some of that was pretty funny." And I think the comedy was actually keeping them more alert, and the question format was keeping them processing things in their mind to understand it better. And so in my mind, that was just a very easy way to communicate in a book, because I know it works in the introductory classroom. So I sort of applied it to the book. But except for the book, I tried even harder to make things funnier than in the lecture, because in the lecture, the most important thing is to teach the material. And here in the book, it's to present the material so it's understandable, but the book has to be entertaining. I realized that if you haven't been entertained in a few chapters, you're going to look at another book. So I tried really hard to make, not every question has a silly answer or a comedy question, but many of them do, because I tried to keep the entertainment level as high as I possibly could.
It worked. I read it cover to cover. Dr. Nemiroff, thank you for joining us today, and I hope you'll come back. Or do you have any plans for another book?
Yeah, I am kind of thinking of a couple books, but at least one book. I don't know if I haven't written anything on it yet, so I'm not going to tease it, because I more motivate myself by doing things to surprise myself that beyond what I said I might do. Whereas if I say I'm going to do it, then I am less likely to do it because I said it, and that's sort of enough. So yeah, I'll just say I do have another book. It might be similar to this book, and hopefully it will be as much fun, but you're not going to see that for a few years.
Looking forward to it. All right, Doctor, thank you, and I hope you'll join us again.
Thank you. Thank you.